Hello, and welcome to this series of videos in support of this Materials Made Smarter outreach demonstration of how computer vision and machine learning can be used to recognize different materials to make recycling easier. My name is Dr. Robert Gibbs, and I have developed this demonstration with Professor Giannetti of Swansea University for Materials Made Smarter. Documentation about the theory behind this demonstration and instructions on how to use this demonstration are available at Discover Materials by scanning the QR code. Also available on the Discover Materials website, an electronic version of the printed booklet and further information about the code, the equipment, and progressively more detailed project documentation. In this third video of the series, we will look in detail through the code that makes the project work. I assume that you have the system up and running in accordance with the first video of the series. We're going to be looking at the code that makes this system work. In order to do that, we're going to restart the kernel and clear all the outputs. So we're not going to be running the code. We'll run each of the cells individually as we run through the code. At the top, we have our banner, bottle, can, or coffee cup, and it's a machine learning computer vision recognition outreach project for the Materials Made Smarter Center. Further information and documentation about this project can be found at the following web address. The project equipment consists of a portable monitor and two combined Seeed recomputers J1010 units housing the NVIDIA Jetson Nano Jetpack project code. The platform this project is built on was based on the NVIDIA DLI Getting Started with AI on Jetson Nano course, and those course information can be found in the classification directory. The first cell of the code launches the camera. If we press Shift and Enter at the same time, or Shift and Return, it will run each cell of the code one at a time. So this just launches the library, the JetCam USB camera library, to support the Logitech C270 camera that this code is designed to run with. We're defining a machine learning task, the bottle, can, and coffee cup task, with the categories bottle, can, and coffee cup. And we have defined three possible data sets, so there's lots of flexibility with how you want to use the demonstration, A, B, and C. These transforms convert the image from the camera into the 224 by 224 array that the machine learning model needs as its inputs. We define the data set for each of those categories, and we create the images directory, which is already present on the system. The next part of the code creates widgets for use in the data collection. We need to import the widgets library and the tradelets library and the display and image translation libraries. We use the dataset that's selected. We just check that the camera is only being run once, so there's no conflicts. And we create a camera widget that brings the camera input in from the library and transforms it into a JPEG image for display on the screen. And this works in real time. It displays the real-time feed from the camera. We create a drop-down menu of all the datasets available. That's A, B, and C. A drop-down menu of all the categories available, bottle, can, or coffee cup. And then a text object that displays the count of the number of images present in each of the folders. And we create a button that tells the system to capture a new image and store it in the relevant folder. The count widget that counts how many objects are in each of the folders is updated to count the actual number of files in each folder. The dataset being used, A, B, C, is updated so that if you change dataset, then the count of the number of images for that dataset is made so that the count display represents the true number of images for that particular dataset. Here we update that number whenever there is a change to the value of the count widget. The save function happens whenever the capture button is pressed, and this takes the image from the camera and stores it in the folder of the correct category in the correct dataset. We then group it all together using IP3 widgets as a vertical box that includes the camera, the camera feed, the dataset drop-down menu, the category drop-down menu, and the count number. Start again. We then group all the data collection widgets together in a vertical box that includes the capture button, the dataset drop-down menu, the category drop-down menu, and the number of images count. We create all of those images. Then we're moving on to loading the pre-trained ResNet 18 model. This is a model that has been trained on millions of different objects, and we're using this as a transfer learning so that we don't need to learn from scratch what an object looks like. The ResNet 18 is an 18-layered model trained on millions of objects to be able to pull out the features for a number of different objects. There are other models that you can investigate if you rem out ResNet and replace them with AlexNet, for example, or SqueezeNet, or ResNet 34, which is an even bigger model. We start with ResNet 18 because it's the smallest of the 4 models and runs best in the limited memory on the Jetson Nano 2 GB. But you can experiment yourself later. We pull in the model. If we have a saved model as a file, then we create a load button and a save button and the path that the file exists at. And on activating those buttons, we either put that file into the last layer of the model, or we save the last layer of the model to the file. This cell takes a while to execute because ResNet 18 is a large model, but eventually it will have loaded that into memory. There we go. It says model widget created. Okay, now we're going to create the real-time interface, the live threading interface that changes between the training state and the prediction state and chooses the change between them. We have our state widget, which displays that difference, whether we're in training or whether we're in production. Okay, and then rather than running in real time, constantly trying to recognize what the camera sees, we've defined the recognize button, so it only performs the prediction if the recognize button is pressed. If the recognize button is pressed, then the image is taken from the camera. It is processed in the transformations to make it the right size and format for the model to understand. Then the output here is the prediction of the model. We just call the model and we give it the processed image as an input. So this single line here is doing our prediction. And it produces 3 probabilities of whether it will be a can, a bottle, or a coffee cup. It'll produce 3 percentage values. And those 3 percentage values are then put through a softmax function, which effectively takes the most likely of those 3 values, the most probable. That's what softmax does. And the category index then becomes the most likely of those 3 categories, the one it has greatest confidence in. The prediction widget then displays the name of the category that matches 1, 2, or 3, the category index. So this live state will provide the live feed of the camera constantly and wait for the recognize button to be pressed before making a prediction. The start live groups together the real-time threading of the model and the camera, the prediction widget and the score widgets. The real-time of the camera happens, but the prediction and the recognition doesn't happen unless the recognize widget is pressed. The predict widget then is a grouping together in a vertical box of the score widgets, which are the 3 probabilities, and the recognize and prediction widget that just organizes the arrangement of the display at the end. In training and evaluation, this is the process where the model is trained on all of the data stored in the images folder. We have an epochs, which defaults at 10. It can be changed. The evaluation button is used when loading a model in. The train button is used when training a model from scratch. The loss widget, accuracy widget, and progress widget are all values that can be interrogated to understand how well the training is performed. In this particular demonstration, I only display the accuracy and the progress widget. The loss widget isn't displayed, but you can choose to display it if you want to. Then this function here effectively passes through each image in the training dataset folders and determines a loss function, which is a measure of the error in predicting that image compared to what the actual image is, and performs the back propagation in order to improve that final layer of the ResNet 18 model. The grouping together of the objects, again to make the arrangement on the display, is the train and evaluation button, the epoch, progress, and accuracy widget. Loss widget's not included. So we can create that widget. The training is only executed on the pressing of the train button. Finally, we group all of our individual widgets together into one widget called the project controls. And finally, we can display the project controls, and we can see all of those elements that were discussed arranged within the project controls interface, with the live camera feed, the data sets, bottles, number of images in each of the categories. There's the 3 categories. We have the train button, which executes the training procedure, the feed that gives feedback on how the training is happening, load model, save model, evaluate if you've loaded a new model, and recognition. So we can load in, we have the model already trained. We can load that in by pressing load. Watch for the little black dot to see that that's finished. Before the model can be used to predict anything, we have to load it in as the final layer of the ResNet model, so we press the evaluate button. This process is faster than just the train. It's starting off just loading the whole ResNet model into memory. But once it's done that, the progress on loading in that final layer is a lot faster than training the model each time. There we go. It's loaded in the model into the final layer and switched itself to the predict mode already. So if we put in an object to be recognized and we press the recognize button, it will create a prediction of that object. And if we put in a different object, it will produce a prediction of that object as well. So loading in the model is a lot faster than training from scratch, as in the second video of this series. The final object to be recognized is the coffee cup it was trained on. In the 4th series of this videos, we'll look at how we improve the performance on objects it has not seen before. I'll see you there.